Hey everyone, how are we doing? No one's in the chat yet. I got all my hair cut off. Oh my gosh, no one's in the chat to even say hello yet. Well, we'll say hello here in a moment. See if anyone joins in. Join in if you're here. Say hey. What are we gonna do to start? Looking over. Haven't streamed in a while. I updated OBS, which was a bad idea. And now I'm like, oh my gosh, OBS is so different. OBS is so different. I want my monitors. Should use standing desks. That'd be really good. Should have got a standing desk a while ago. All the coulda, woulda, shouldas. Let me get the notes open for today. What are we gonna do? What work are we gonna do? No one's in the chat yet. What assignments should we do? Go look at the schedule for Stat 201. Oh, getting McGraw-Hill sending stuff about. Join us to use R. UTK not working? What? UTK is totally working. No one's here yet. 201. Oh, let's take a look. I'm not drinking coffee, so people are getting the grading done. Oh, need to talk to section 1. Need to make sure those get graded. Let's go look at the syllabus and see when test 2 is. Download. No one's here yet. Everyone said spring break's over. What? No. End of the semester just flies by. Like when we get to the end of the semester, it's just whoo, done. Let's go look at that. Okay. Maybe I'll decrease size right here. Pew, pew, pew. A little more to the right. There we go. Nice and on the edge of the screen right here. We love that. Okay, so we ended off right before break right here. That's where we ended off. And the second exam is tentative for Tuesday 4/4. So that is not a week from tomorrow. It's 2 weeks from tomorrow. Holy mackerel, we got a lot of time. Well, I guess, are we doing both sampling distributions now? Yeah, we are doing both sampling distributions. It's kind of like, that means we should maybe spend a whole week doing sampling distribution part 1 this week, and then sampling distribution part 2 the following week, and then reviewing. It's tough stuff though. So I mean, that might be the best. From readiness to these are tough chapters right here. So maybe I'll do a review of those chapters right now, like understanding sampling distributions. I wonder if anyone will find the videos for that. There's my zoom in. I need to get everything back working here again. Updated, never update but during a semester, but we're doing a presentation. So I updated to be like, let's get this on the latest version of OBS. So when I'm working with people, we can have the latest version of OBS with them. Because you don't want to be like, explain to people how to do stuff and be like, oh, I'm 2 versions back. You're using OBS version this, well, I'm using OBS version 3 versions back. I said 2, now it's 3. But yeah, is anyone in the chat yet? No one's in the chat. Talk about some sampling distributions. I feel like no one's gonna be able to find this then. Sampling distribution homework. Talk about it here just a little bit. This is one of the toughest chapters. So Stat 201 sampling distributions. Sampling distributions. Let's put the timestamp here. 6:03. Stat 201 chapter 13 homework. Sampling distributions. Okay. Let's go check it out. Here we go. So this, a lot of times, is a very tough chapter field. Chapter 13 and 14 are covering 2 main ideas: sampling distribution of the sample proportion and sampling distribution, gotta see your T's, sampling distribution of the sample mean. So with this one right here, an investment website can tell what devices are used to access their site. Like, was it a smartphone? Was it an iPhone? Was it a Galaxy phone? The site manager wonders whether they should enhance the facilities for trading via smartphones so they want to estimate the proportion, which means it's categorical. That's a key note to have right here. I always say we should maybe do that. Underline the important stuff right here so we know what we're looking at. So let's go over here. 2 seconds. Let's get the notes on the screen. And let's take a look. So the first thing you're going to see right here is key parts to this question that we need to take note of. And when you see things like the proportion that means you're working with a categorical variable. Like, do people own a cat or dog? Is the proportion of people owning a cat or the proportion of people owning a dog? Proportions mean yes, no, categorical questions. Is someone using a smartphone? Is someone not using a smartphone? Is categorical, i.e., leads to the proportion of people owning a smartphone. They draw a random sample. So this right here is the N, which is the sample size from their customers. Suppose that the true proportion, so now they're telling you P is equal to 31. So proportion is often expressed as a decimal right there. So these are all the notes we have to do this question. There's additional things we can find though. So as you work through these questions, you have to identify what's important and what's not. This question could be any sort of question. We would know that Q, which is the proportion of people who don't own a cell phone, is 69%. So when you work through a question like this, notation is going to be key. What is the proportion of people who do own a cell phone? And that means, like, in actuality, like if you were to poll everybody, that's the proportion of people who actually do own a cell phone. And this is the proportion of people who actually don't own a cell phone. And the thing is, it never mentions what's the size of the population. Now, that does not stand for N for normal. That stands for capital N for sample size. And the population size. Population size is everybody, like all people in the United States, where we might have a sample of 118 people, which is just a small subsection of our population. Now, from our sample, we would get the amount of people in our sample who had a cell phone, which might be like 20. And then if we do 20 over N, we would actually get P hat. And this is very important right here, this sort of notation. And a lot of times people are oftentimes confused between P hat and P. So the difference here is P relates to a population. So P is the true proportion. It means for all people, for pretending we're talking about the United States, for all people in the United States, 31% of people own a smartphone. But then P hat is for a sample size. So when you talk about P hat, you're saying percent or proportion of people in our sample. Very important. And to find P hat, it's X over N, number of successes over number of samples, and that will lead to P hat right there. So this is more of a breakdown of this question. One last thing we could find is Q hat. Q hat is 1 minus P hat. So 1 minus P hat, they're called complements of each other. So we go right here and we find P hat, and this is just hypothetical for this question. There's P hat, which is about 17%. We're going to round it. So P hat was equal to 17%, and Q hat would be equal to 83%. Now, I made up a lot for this question to solve additional stuff to show like everything we could solve. It could tell us the size of the population, like there's 10 million people, and then we could figure out how many people in the population own a cell phone using the proportion of 10 million. It's important to understand what the notation means, that is the sample portion who do own a cell phone is 17% from our made up 20 people in the sample of 118. This is the proportion who don't own a cell phone, which is 83%. And now we can get to the question. This question actually deals with the sampling distribution of the sample proportion. Now, there are three conditions. The three conditions are 1, where's that? Random. 2, 10%. And 3, success/failure. Now, memorize these. The first condition for the remainder of the semester from here on out, this point, is going to be random. Be careful. We're still doing regression, so you need to remember to do regression, which has different conditions, which is QQ straight enough, no outliers, plot doesn't thicken. But after, or this chapter and beyond, the first condition is always we randomly sample. So as long as they took a random sample of individuals right there, which it does say random. So I like to make sure we see these things as we do them right here. It says random. So that's random. 10% means we sample less than 10% of the population. So if we're sampling the United States, 118 individuals would be less than 10%. This one's a very confusing condition. It actually works with finite populations and how we have more error when we oversample. So it's a really interesting mathy one. I don't get too much into detail with it because I pretty much put people to sleep with the details. But the way to check it is your sample size less than 10%? So you're asking, is N less than 10% of your population? So that's what we're looking at right there. And the answer is probably yes. It's logical to say that. And last but not least, we have the success-failure condition. Now, the success-failure condition right here is very important on how we do it when we know the truth. When we know the truth, we do the following equation. We do NP is greater than or equal to 10, and NQ is greater than or equal to 10. And we already have a lot of these notations from the problem. We have P, we have Q, and we have N over here. So we're literally just going to plug in the numbers where we put in here 118 times 31%, and then 118 times 69%. And these need to be greater than or equal to 10 when we solve them. So you want at least 10 successes, at least 10 failures. And the reason we use 31% is because we're using the truth. And I'm going to round this to 37. Now, what's interesting is that these two numbers right here will add up to 118. So I'll show you how to get the other one. 118 times 69 right here. And there it is. It's basically 81. And then we rounded them. Don't round them when you're usually solving it. But if you take 81 plus 37, you get 118. And that's because we're taking the proportion we expect to be successes and the proportion we expect to be failures. And if you look at the two right here, this adds up to 100%, and you're basically taking 100% of 118. You're just breaking it into two parts. That's how the mathematics works. It's the amount of successes you expect and the amount of failures you expect. Hey, what's up, Reed? I got a haircut. We're showing off some chapter 13 right here. And what's really cool is I really like this condition. I'll show you why. Binomial. If you got question reads, let us know. I said reads. Binomial applet. So think about this. And this is how the condition works. Thank you, Reed. I appreciate that. I got a second haircut. The first one had like a floop in the front. So if you saw me during the event, I had a floop. Now I've got like normal guy professional haircut. If we were to talk to 100 people, and let's say 1% of them had a master's degree, what percent or what amount of people would you expect to have a master's degree? So if we were to talk to 100 people in our sample, and 1% of people in the United States have a master's degree, or let's say PhD, what amount of people would you expect to have a PhD? And it actually shows you the math down here. So if you look, we talked to 100 people, and 1% is the true proportion that have a PhD. So if we talk to 100 people, and the true proportion of people who have a PhD is 1%, that's what P stands for. So in the United States, 1% of people have a PhD. We talk to 100 people. How many people would you expect to have a PhD out of the 100? So we talk to 100 people. That's what N, 1, right? What if we talk to 200 people? How many people would you expect here to have a PhD? So we talk to 200 people, and 1% of people usually have a PhD. So we expect around 1%, but how many people? 2, right? So you know what's interesting? As I keep increasing this, what do you notice this distribution is starting to become more like? As I creep up, really? Oh, it's mad because I didn't put a... What do you notice it's starting to look more like? As I keep increasing this, it's starting to look more and more what? I'll make it... Is it going to break? Sometimes it break. Oh, it does. I hate it that it does that. It starts to look more and more normal. Exactly. So what we have right here is if we have at least 10 successes, at least 10 failures. So if you have at least 10 successes, at least 10 failures, so now 5% of people have master's or PhD, and we talk to 500 people, we'd expect 25 people. And this is found just by doing N times P, which is what we were doing over here, N times P to find out the answer of the expected successes and the expected failures. If we meet all the conditions, then it will be normally distributed, which is unimodal and symmetric. So all of this work right here to talk about it. But here's the thing. All the work we just did for this question is pretty much most of the work for this whole chapter. What would be the mean of the sampling distribution? Well, the mean of the sampling distribution is mu p hat is equal to p. So wait, just look at my notation. What is the answer to the question? So read through what I have right here, read. We're looking for the mean of the sampling distribution, and that is equal to P. So what is the mean of the sampling distribution? So the mean of the sampling distribution, which is mu P hat, because this reads the mean for the distribution of the sample proportion is equal to P. So this is what we want to find, and this is the answer. So do you know what the answer is? I've got it all my notation marked here. If you don't know, that's all right. I'm throwing you some 100 points read here. And then when you start to realize how to do these problems, you're like, wait a minute, that's it? You don't multiply. So this is a full notation here. This is read the mean of the sampling distribution, but the answer to the question is P. So what this means is imagine it this way. If 1% of people have a PhD, what percent of people would you expect to have a PhD in your sample? Don't overthink it. Not those. Good answers, good guesses, Reed. But think about this: if 1% of people have a PhD, and you go out and talk to people, what percent of people would you expect to have a PhD? So the mean is the expected sample proportion. So if 1% of people have a PhD, and you talk to people, what percent would you expect in your sample to have a PhD? Don't overthink it. Be like, okay, if 1% of people have a PhD, and I talk to people, what percent of people would I expect to have a PhD? Percent. No sample size given. 1%, right? So if 31% of people have a smartphone and you go out and talk to people, what percent of people would you expect to have a smartphone? If 31% of people have a smartphone, like that's the truth. Like when it says P right there, that means it's the truth. So if you look up here at the question, it says that's the true proportion. So 31%. Yep. And then make sure to enter it in as a decimal. But right here we go. And that's it. That's that answer right there. The problem is a lot of times people realize, so understanding the theory behind it's the most important part, to be like, okay, if 31% is the truth, then I should expect to see 31% because that's the truth. That's the most likely thing to see, which when you draw the distribution of it, it would be at the very center of the curve. So let's go over here to our apps and show what this would look like. Anytime we draw the sampling distribution, we need a mean and we also need a what? Anytime we draw a distribution, we always need a mean. And what else do we need? We need a mean and we need a what else? A standard deviation. So we know the mean, which is the expected. And let's bring this down a little bit here so we can actually see where it's at. The mean is right here at 31%. So we would say if 31% of people have a smartphone, well, then we would expect to see around 31%. And I'm putting it right there so you can see where 31% is at the center. Now with this, to find the standard deviation, and you get these formulas on the test, the formula is P times Q over N square root. So the standard deviation of P hat is equal to P times Q over N square root. So now we just plug in our numbers. We know from the previous problem, P is 0.31. It told us that. Q is the complement of this. It said we sampled 118. You can see it up there where I was using the sample size over here from the problem, and we square root. So we do P times Q over N square root. And guess what? That's the answer. And we plug it in here, and we can see what the sampling distribution looks like. So there's the sampling distribution. And other problems will have us go more in depth with this. But now we go ahead and round this right here. We check answer, and we did it correct. And that is the majority of this chapter. Knowing how to check the conditions, knowing how to find the mean, knowing how to find the standard deviation. That first problem right there covers a lot of the whole chapter. So we just did a whole chapter kind of, not completely, like I didn't go into great detail. We haven't done other problems where we ask like what's more likely, this or this. But that's a really strong problem. Sometimes, I'm critical of my Pearson, but that is about as good as a problem can get for doing the basics of the chapter. Checking the conditions, knowing what the shape of the distribution will look like, and also finding the mean and standard deviation. And probably they should have you draw the distribution too. So this problem right here is very similar, where it reads, let's take a look right here. In automatic character recognition. Happy Monday, Colin. I got my hair cut. We're going to plan out some awesome stuff. Good to see you here. Thank you so much for swinging by. Let's throw out 100 points for some pixie dust. Thank you for the haircut compliment. I appreciate that. An automatic character recognition device successfully reads about 83%. So they're telling us probably what P is, the proportion it successfully reads. To estimate what might happen when this device reads a stack of applications, the company did a simulation using these right here. These are all different sample sizes N. For each sample size, they simulated 1,000 samples. So they did 1,000 trials. Okay, so with the success rate of this, construct the histogram of 1,000 samples. Proportions, explain what these histograms say about the sampling distribution model for, yeah. Okay, so yeah, they're doing this at 20, 50, 75, got it. And so what's interesting with this is if we have 83% success rate, well then over here at 100 times we're doing NP, and the more important one's going to be NQ because Q is equal to 17%. That's because P and Q are complements. So P is equal to 0.83 and Q is equal to 0.17. So if we really only need to focus on Q because that's the smaller one where we're going to have less than 10. And this is one of the conditions, the success failure condition we just mentioned a moment ago, that we need at least 10 successes, at least 10 failures. It obviously fails for 20 down here. With 20, times that by 17, you're going to only have 3.4 successes, I believe. Just doubling it right there and moving the decimal. So 20 times 0.17, there we go. And right here at 50, we're probably getting close. 50, we can take half of it if we're doing some mental math right here. And so that's going to be 8.5 successes. So check our math. There we go. So that is right. And then 75 is where we're going to start to see that it has at least 10 successes. And that's all we're really checking for right now, because when you get at least 10 successes, which we will have right here, so it's a half of a half, so it's going to be 12.25. Ooh, no, I moved a decimal, I think. 75 times 1. 12.75. So that's at least 10 successes are expected now. And the reason we care about this is if we don't have enough successes, which could be down here if we only had 20 trials, the distribution will not be normal. We can also model it over here. It said, what, a 17% failure rate? So here's with 20 trials, there's only 3.4 successes, 50 trials, 75 trials, and at that point it's normal enough with at least 10 successes right here, the expected successes. And then we have over here at 100, it's even more normal. If you only did 10 trials, it'd be very much not normal. Yeah, which one do you want to do, Reed? Tell me which one you want to do. Let's do some Chapter 8 quiz stuff right after this one. You got it. So that's what this question's getting at right here with all this theory. And let's take a look. What is the shape of 20? The shape will be skewed to the right because it's going to go towards the higher. Oh, it's skewed to the left. Let me explain why it's skewed to the left really quickly. It's because we're talking about the 83% success rate, and it's going to be skewed to the left right there. So it is going to be skewed. Correlation between cell phones, you got it. So that's going to be skewed to the left. The sampling distribution is centered around, that's where they have you view it. Oof. This one is a fun one because you have to look at these exact bins right here. 6, 7, 8, 8 to 8.9. You have to use the bins it shows you. 8 to 8.9. And the sampling distribution has a range of about 0.5. Greater than that, check answer. Okay, this one, a little bit detailed. The center is 0.7, 0.75, 0.8, 0.8 to 0.85. There's where the peak is at. So it's a little skewed to the left. Better say that. 0.8 to 0.85. And the range is 0.35. For the range, if we're seeing how I'm seeing that, I'm looking at this distance to this distance. The range is the max to the min. And it's about that because the bins are a good estimate, but not precisely, but that's all the information we have. So it's about 0.35, which is in this range right here. There we go. And now we're going to say it's normal because it has at least 10 successes. It has at least 10 failures. So where it gets a little tricky with the bins. That's 0.7, 0.75, 0.8. So 0.825 to so the 0.8, oh, it's going to be approximately normal. 0.825 to 0.85. And then the range is 0.35 again between there. There we go. Has that got it? Whew. And the last one is only 0.20 for the range. That's easy. And it's going to be even more normal. That's easy. And then, so 0.20. Where's 0.20? Right there. And then the center of it, it's on the in-betweens. This one I'm worried about. If you were to get this wrong, just tell me, like, I'll fix this. I might get quite a few meals on this one. It's really hard to tell exactly where that's at. The truth is it's going to be around 0.83. 0.83 must be included in the bin. So since 0.83 must be included in the bin, that's going to be the answer right there. So quick way to tell the answer right there, because the truth is where the center is at, and it's a lot more normal. So a little tough there, especially at the end, but 0.83 or 0.84 this time. So this one's even tougher because 0.84 is on 2 bins right there, the 0.84 to 0.86 bin. So if you were to have something like this where it wasn't right between like mine, then that would be a little bit tougher. So good work, but 0.84 should be in all these bins, but sometimes it's on the edge of one, so you have to look where the peak is at. So you have to see, here's the peak here, here's the peak here, here's the peak here, here's the peak here. And truthfully, the answer is always around 0.84. The peak is always around, well, whatever the truth is. Last time was 0.83, but there's where the truth is at. Awesome. Let's do another question right here. Heading back with the main screen. 2 hours later. Correlation between cell phone usage. Chapter 8 quiz. We got so much time. When is the next things due? Sampling distributions are on the 24th. Okay, good. Means we get it done this week and get the next one done next week. And there we go. And then we got to start conference rolls pretty quickly, because what is the test again? Wait, is the test on the 4th and we have a homework due on the 4th? No way. Why would we do that? Well, I gotta move. Let me move that right now. Wait, conference rolls for sample proportions. Okay, that has to be moved. 2 seconds right here while I move a assignment that is due the night of the test, it looks like. That is ridiculous. I think let's go there. The 11th. I should tell Terry too. Like, I think we have something to do the night of the test. Your students are not going to do that. Let me take a screenshot of this. And then we'll do the next question. It's interesting. Yeah, it's... Oh my gosh, I gotta tell Terry about this. It opens one day. I gotta be like, hey Terry, this right here. Let me email him right away. Okay. And okay. Is there any evidence? Of course. Correlation between cell phones. Let's go grab that one here real quick. I emailed Terry right there. It's due tomorrow. Correlation between cell phones. All right, let's go check it out. Here we go. Correlation between cell phones. Is this it right here? The correlation between cell phone usage should be very high. And then we'll do the next one here. Awesome. Stat 201, chapter 8 quiz. Okay. The correlation. Okay. So should it be the first? No. Oh, let's take a look. The correlation between cell phone usage and life expectancy is very high. Should we buy cell phones to help people live longer? This is totally talking about lurking variables right here. No, this is probably correlation is not causation. Lurking variables. People with money have cell phones. No, cell phones are easier to obtain for people who are relatively wealthy. Okay. And those who are relatively wealthy typically have higher life expectancies. Since there is a lurking variable model, cell phones should not. That kind of makes sense. No, cell phones are expensive, and there are no. Yes, correlation. No, So yeah, they're talking about a lurking variable. That's a good one right there. Lurking variables. The best way to think about a lurking variable, I always like to do a little bit of a lecture, especially for short questions, is when you have a lurking variable, you have right here your x variable, your y variable. And it looks like x and y are related, like cell phones and life expectancy. And so it could be life expectancy leads people to buy cell phones, or cell phone leads people to buy gets a longer life expectancy. But it turns out something like a z variable right here, like wealth, might actually be impacting both of them. One of the most famous examples we have are shark attacks and ice cream sales. So you have here shark attacks and ice cream sales. Ice cream is with an I. Ice cream sales. And the lurking variable is summertime. Because when it's summer, there's more ice cream sales. And when there's shark attacks, it's usually summer. So it's not that shark attacks increase ice cream sales, or ice cream sales increase shark attacks. The lurking variable, the variable outside the XY paradigm, is going to be summer right there. So that is what we have going on with the lurking variables. It's a variable outside the XY variables, and they're identifying a lurking variable here. It's not cell phones increasing life expectancy or life expectancy increasing cell phones. It's probably wealth increasing both of them. So pretty good lurking variable question right there. Is there any evidence? And also identify them as names, like be like, that's a lurking variable. Is there any evidence? The age at which a woman gets married. Let's see. 3403, Stat 201, Chapter 8 quiz. Is there evidence that the age? Okay. Is there evidence that the age at which a woman gets married has changed over the past 100 years? The accompanying Scatterplot shows the trend in age, first marriage, or trend in age at first marriage for American women. Complete parts A through D below. Oh, this is very much a non-what. What's the problem with this, with what we've been learning? You see this immediately. This data was collected every 5 years to start, but then there's some major issues on this. Like, you should see this and know major issues immediately. It's nonlinear, exactly. It's not such a big deal at the start that they were collecting every 5 years. That's just a data collection thing that they went from 5 years. It looks, that's every 10 years. I'm just going to throw my pen and lose it. There we go. So every 10 years to start, because you can look here in 1900, 1910, 1920, then it looks to be about every year. But there's major nonlinearity in this. So that's probably where they're going to go with this question. Is there a clear pattern? Oof, there is. There is a pattern. Remember, linear is only one type of pattern, so don't be like, oh, there's nothing going on here. It's just non-linear. The trend appears to be linear up to. No. The trend appears to be non-linear. Yeah, they're going with that, aren't they? The trend appears to be non-linear up to about 1970, and from 1975 to present, the trend appears to be linear. So if you go here to about 1975, there is at this point a kind of linear up. So there is a linear trend there. And this is the age? Sure. Interesting. Is the association strong? Yes. The reason the association is strong, this is where a lot of people will probably miss this, is strength of a relationship is the degree to which the points are scattered. So the scatter around a line or a form is the strength. So this right here is very strong. That parabolic form is very strong because it's very tight. This line right here that I'm drawing would be weak because the points are scattered around it. So I'm looking at the scatter around a possible line, or also the nonlinear scatter, but it's very tight around it. So the tightness of the points, how tight they are around the form, but the form can be nonlinear, so it appears to be relatively strong, and I feel like a lot of people will miss that one. Is the correlation high? So this right here, no, as the whole graph is clearly nonlinear. Remember that linear is only, correlation is only measuring linear strength. Really good connection between the chapters right here. I love it that this brings back a chapter 6 question right here, which is very important that we know correlation only measures linear strength. So when we think about correlation right here, if we were to look at it, the correlation would not be very strong because there's not a good linear form throughout the plot. So that's the issue. Is a linear model appropriate? No. Let's see what the other no says. No, a linear model would not be appropriate throughout, although one could fit a linear model. Yeah, that's called piecewise regression right here. Piecewise regression is when you take part of this and fit, which is interesting. They bring it up right here, but they're saying you could maybe fit a line from here out. Yeah, possibly. It's not the best, most perfect line, but about at 1975 or higher, you could fit a line that would probably do pretty well. We should get 100. Show me that 100. There we go. Really good question going into a lot of the issues. Does that make sense, Reed? Good to see you here, Kelsey. But think about the different issues that can arise. A little tricky at the end right there because you could theoretically do that. But it's funny sometimes. I hate it when they do this. This is like, we have a little problems with my Pearson. Well, sometimes I have a problem with this test we write. Chapter 12, you bet. Let's do some chapter 12. There's one on gestation. Here, we'll do that one next, and then Caitlin will do yours because we're here on chapter 8. But thank you, Caitlin. Let's throw 100 points for everyone being here. When you look at these answers, yes, the model is appropriate is the worst answer possible. No, the model is not appropriate. The next best answer would be no, and then a more specific, good to see here, Stacy, a more specific no, like, yeah, no, but we could do it for like 1975 going forward. So there are like better ways to answer than just no. So pretty, the no, but we could do it for 1975 going forward. Let's see. The gestation question. 3-month bills. Good to see everyone here. We got a bunch of people in office hours now. Animals' gestation periods. Is there any evidence? We're rocking and rolling right here. There's all these. Is there any evidence? It's like the main theme of all the questions. Is there any evidence? Pretty funny. That's how we do things in statistics. Here we go. Is there any evidence that an animal's gestation period is related to the animal's life expectancy, lifespan? The scatterplot shows gestation periods in days versus life expectancy in years for 18 species of mammals. The highlighted point on the right represents humans. Complete parts A through E. So there we go. There's humans over there, and we literally have something breaking the trend. What condition is this in regression that we are missing right here? What condition do we have problems with humans? Including humans would cause a problem with which condition of regression? So I'm asking you to think about the regression conditions. So we got, there's the first condition, there's the second, there's the third, and there's the fourth. So what were the 4 conditions, and what conditions do humans break? So remember, we're here to review also. So you should know the 4 conditions of regression, which I just kind of drew. So I kind of can draw on the plot and check the 4 conditions. It breaks outliers. Great job, Reed, there for 100 points. So the 4 conditions for regression are, and I'll say them this time, so you might have been saying them too. QQ, which means 2 quantitative variables. If you have a scatter plot, you got that. Straight enough means a straight line will approximate the relationship. No outliers means we want no outliers, and plot doesn't thicken means we want relatively the same thickness throughout, which is a measure of strength. So it does mean that humans are a problem with outliers. So for the data point right here, the correlation, that's what R equals. This is not very strong. Do you think the association would be stronger with humans removed? Most definitely. There's with humans removed. Here's with humans not removed. So when you remove humans, you get a tighter cluster of points. So it would be stronger. It's a ridiculous answer that it's easier to fit points through fewer data points. No, it's the correlation would increase and the slope would increase also. Slope doesn't indicate strength of relationship, but the slope does increase also. Strength of relationship is tightness of points, and the points would be tighter right here. So we could have a point way over here that would, including that point, would increase the slope, but it would decrease the correlation because the points would be more scattered out. Okay. Is there reasonable justification? Yeah, if we're talking about non-humans. So you could restrict it to non-humans. Not much of a learning objective right there. But remember, we sometimes have reasons to remove outliers. That's kind of the review right there. Sometimes someone can be like, yeah, let's not include humans in a data set of animals, which we're animals, but let's just restrict it to non-humans. Be like, dogs, cats, cows, emus, whatever. Here's the scatter plot right here. The association is what? Now, it's not perfect. Perfect would mean every point is directly on a line. That's impossible. Well, not impossible, but not possible here. Moderately strong means decently tight, and moderately weak means decently scattered out. This is moderately strong right here, especially since we know the correlation previously was 0.54, so it would be even higher now, maybe 0.7. So it's definitely, and we have the R squared, so you know what we could do? If we really want, we could take the R squared right here and find the correlation by going to 0.869 and square rooting it, and it's 0.93. So I wouldn't even say moderately strong. I would say it's probably really strong right there. So that is a really strong correlation. Interpret the slope of the line. So the slope right here is the coefficient of the x variable right there. So the slope is going to be this one over here. And let's take a look. The slope would be on average for each year in life expectancy. The gestation period is expected to increase by about 13 point, and it's just 2 decimals, 0.04. There's the interpretation of the slope. For each 1 unit increase in X, life expectancy, we expect Y to increase by about B1 units, which is down there. A certain mammal has a life expectancy of 29 years. So this is where we need to write out the equation. So we take the notation right here, and we remember that this is going to be equal to B0. This is equal to B1. And then we write out y hat equals B0 plus B1x, where x is going to be the life expectancy, and then 13.04, and then we do 94.03, and this is going to be the gestation period right here, and then we plug in the numbers. So let's go ahead and plug in and carry the decimals. I think it said how many years? 29 years. So all we're doing right now is taking 29 and plugging it in right there to where x is. So let's do it. 29 times 13.04. Oh, let's carry the decimals. 29 times 13.0422. And then let's add to it 94.0281. There we go. Carry the decimals, go over here, then round to 1 decimal place. Usually they're pretty nice about this. Like, I shouldn't do that. I should round up as it says. But usually they give a little bit of leeway if you didn't carry all the decimals. Once again, if you're off by like a 0.1 on a lot of these, I give points back. Be very careful, especially on the T questions coming up later in the semester. Those you don't get points back for being very close because the T curve is very different from the normal curve. So good stuff right there. With that, let's head over, and Caitlin, time for your question. Let's do it. Wrong button. Okay, Caitlin said, oh my gosh, what we got going on the screen? I turned off the marble. I got them. Okay, so Caitlin said, can we do chapter 12, the Mars Candy Company? Oh, this is on, ooh, this is a long one. Ooh, good question. Remember, if you're seeing this later, swing by office hours and get some work done. So, chapter 12 quiz, the Mars Candy Company. This is a tough one, Caitlin. Good choice. Let's see. This one, it's like, what's the probability of selecting like a blue and green? It's a very tricky one. Okay. There we go, the Mars Candy Company. $100 yards. Which one is that? That's from chapter 8, right, Maddie? Here we go. We found the Mars Candy Company. It's from chapter 8, right? Let me know which chapter it's from. I think so, right, Maddie? The cyclist one, that one gives you the date, I think. Awesome. Here, we'll do that next. Remind me if I don't do it, but we'll do it here. So this one starts off giving you a sampling distribution, and be very careful because you can make errors on this. So what you want to do is you want to write out the valid sampling distribution. And I've made errors on this one before. So do not make errors like Brian's about to make, like somehow deleting your thing. Okay. How did I delete that? Well, who knows? Okay. Before the introduction of purple, yellow candies made up 20%. So we have here the event and the probability of the event. So we have here yellow candy, and that's going to be 20% right here. Next, we have red was 20%, so red's going to be 20%. Orange, blue, and green each made up 10%. So orange, blue, and green. Orange, blue, and green. The rest were brown. Okay, so brown. Okay. And so what percent were brown? So what percent were brown? What percent were brown? What percent were brown? This is the key right here to solving these questions, to know how a valid probability distribution works. The rules of probability say what? So it's given us all the colors. And so for this to be a valid probability distribution, we can solve for brown because we should know it's what? So we have all the things that can occur. This is the sample space. Great job, Caitlin. Yep, 30%. Because it is the remaining portion, because we know all the other colors. So what's the probability right here? It's 1 minus all the other probabilities, or we can just add up to get 100%. So you want to make sure this adds up right here if you have everything listed to 100%. Great job, Caitlin. Worth 100 points right there. There we go. Okay, so now that we've got this written out, we can start to break down the questions. Here we go. I'm going to put up a side-by-side screen of this so we can kind of work it side by side right here. It might be a little small. Let me do this. We're going to try to get this side by side so we can view it over here. Zoom in on it. There we go. Look at that. Okay. Got our little cheat sheet right here. Look at that. Perfect. And then we're going to bring this in. We're going to move that. And then bring this over here and increase font a little bit. Okay. What is the probability in M&M is brown? The probability in M&M is brown is just going to be the simple 30% that we found. What is the probability it's blue or yellow? So here's the key to this question. When you get an M&M, can it be blue and yellow at the same time? We're doing a lot of review with this. Can an M&M be blue and yellow at the same time? Like you pick up an M&M, is this M&M right here blue, and can it be blue and yellow at the same time? So what can you do to the probability of blue and yellow, not blue and, but blue or yellow? What can you do to the probability of blue or yellow? Since they're disjoint, you can do what to their probabilities? What does the rules of probability say you can do because they are disjoint? Because they are disjoint, blue and yellow can be what? What can we do to blue and yellow? So what we can say the probability it's blue or yellow is simply what? What can we do to their probabilities? To find the probability of blue or yellow, we can simply what? Give it a moment longer. We can what their probabilities. This is a singular M&M. What's the probability it's blue or yellow? Add them, exactly. So blue or yellow is just going to be adding up the two probabilities. So blue was 10%, yellow is 20%. So we just add them right there and we get 30%. Not orange. Well, when it comes to not orange, orange is 10%. So what's the probability of not orange? It's the complement because either it's orange or it's not orange. So what's the probability of not orange? So orange is 10%. What's the probability of not orange? So if orange is 10%, what's the probability of not orange? 90, exactly. And then stripe doesn't exist, so that's impossible. Right there. Now we get to the harder questions. assume you have an infinite supply of M&Ms. So they're saying you could just infinitely, it's not going to change the ratio of what the probabilities are. Suppose you pick 3 M&Ms in a row. What is the probability that they're all brown? So this means the first M&M was brown, and the second one was brown, and the third one was brown. So each M&M would not influence each other, meaning each M&M is what of the other M&Ms. Each M&M is not going to influence each other, so it means they're what of the other M&Ms. So each M&M will not influence each other because you're going to draw an M&M, you're going to look at it like it's brown. They're independent. Great job, Caitlin, right there. Those are the keywords to know. So we can actually do what to these probabilities right here. So since they're each independent, we can what these probabilities, which is what we have to check before doing this. To say, oh yeah, the M&Ms are not going to influence each other. They're each independent. We can multiply. So what's the answer to this question? What will be the probability of 3 brown M&Ms in a row? So we basically have it written out, but what will the probability be? You're right. Great job, Caitlin. There we go. Just multiply that out, and that's the answer. 0.027. The problem is this. Okay. Let me make sure this is where it gets a little tough and a little tricky. The probability of the third one being the first green one. Okay. So it would be not green, and then not green, and then green. Okay. So we have to get a not green, green. So what is the math here, Caitlin? So it would be the probability of not green, and then green. So the probability, the third one is the first green one. So it'd be the probability the first is not green, and the second is not green, and then the third is green. So if you can write it out as mathematics, this is using the complement of green. So a little tricky right here. Yeah, Caitlin, you got it. There we go. And that should solve out to about 0.081. No, it should be smaller than that. Is that it? Let me double check. I think it is. No, what am I doing? I did something wrong right there. That's why it's always good to do things in your head. There we go. That's it right there. Awesome. Double check your work. Okay, the probability that none are blue is this. Okay, so none are blue. Well, that's not hard. The probability that none are blue is what? So we'd need not blue. What's the probability none are blue? So the probability none are blue. The first was not blue, the second was not blue, and the third was not blue. What's the probability none are blue? Yep, I think so. So, because that's the probability of not blue. There we go. There it is right there. Now for the last one, the probability at least one is orange. Okay. So we either have none are orange or at least one is orange. And this is the tough part of these questions for these complement questions. Either none are orange or at least one is orange. So let's figure out the probability of none are orange. What's the probability that none of the M&Ms are orange, Caitlin? Which is going to be interesting because it's like the last one. What is the probability that none of the M&Ms are orange? So we need not orange times not orange times not orange for the probability none are orange. So the probability that none of the M&Ms are orange is what? So you have to look at our probability table and you have to say what's the probability it's not orange, not orange, and not orange. It's the same probability because it's like blue. And so with that right there, we plug this in and then we can solve because we can just do some algebra right here and bring this over to the other side. And when we bring it over to the other side, we can find out the probability at least one is orange. So the probability at least one is orange is that right there. It's the complement because either none are orange or at least one is orange. That's probably the hardest part of these questions right here is writing statements like this. Either none of my M&Ms will be orange or at least one will be orange. One of those things must occur 100% of the time because they are complements. None are orange or at least one are orange. And there's the probability. We should get everything right. Let's hear it here. Type an integer, do not round, check answers. 100%. Woo! It's a tougher question. Caitlin, does that make sense? This question right here really goes over the multiplication and addition rule and the complement rule. It's probably one of the best questions there is for this. You have to be very, 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 very careful on it. And the best way to do these questions a lot of times is to write out your distribution right here and to see everything. Make sure you know what a sample space is, all the things that could occur. Make sure you know the sample space adds up to 1, which is one of the rules of probability. All probabilities are contained between 0 and 1. We use the complement rule. This literally did every rule of probability. Caitlin, 100 points. Really great question for people to go over and learn how to do. So great job. And the next question was, I think Maddie said the 100 years. Let's go do that. 100 years ago, the fastest cyclist. Okay. 100 years, the fastest cyclist. Let's take a look. Chapter 8 quiz. The fastest cyclist. Here we go. 100 years ago. Note on it. Stat 201, chapter 8 quiz, 100 years ago. Let's go check it out. Here we go. So this one right here, we need to use jump for. So let me get jump up and going while we talk. Jump is going to be a huge help for this problem. You will sometimes see jump output on the test, so I highly recommend knowing how to read jump output because it'll be a huge help for you solving problems. Okay, I need to get jump 17 on my computer. It hasn't really changed much since like jump 13. So what we're going to do is we are going to take the data right here. We're going to go to the data sheet. And we are going to go to the top right here and go to copy to clipboard. And then we're going to hit Control C. If you notice, it has column names right here, the year, the winner, the average, the speed. We're hitting Control C to copy it. Then we go inside of Jump and we go to File, New Data Table. File, New Data Table. Yeah, Reed, which one's chapter 8? Cool, we'll do it here. Under the New Data Table, which you'll be in right here, we're going to go to Edit and then Paste with column names. Paste with column names. Whoop. And there you go. Now, if you don't see blue, you've done it incorrectly. Winner is a name which is not an identifier because it does repeat. A lot of Lance Armstrong down here. There, look at that craziness. 1990. I didn't know he won in the 90s. I remember the 2000s. So with that, there you go. Let's take a look at this by going here to Analyze. And under Analyze, we are going to go Analyze Fit Y by X. Analyze Fit Y by X. And we're going to put year as the explanatory variable and then average winning speed as the Y variable of interest. And let's go ahead and click OK. And we can see the pattern right here, which is the first thing we have to identify. So let's see if we see any weirdness. We don't see these dips at the end. Well, I don't know if they changed this question, but without any sort of weird dips at the end, it's rather obvious that it looks like this is the pattern because there's no real crazy dip. That's weird. Well, I don't know if they updated it, but that's the answer to the question. Now, describe the relationship right here. There is some oddness to this data. I believe you've got missing data inside of here. If you look, we might be able to highlight the point, 1919, and then right here, 1914. So there's missing data there. And there's a huge gap right here for the Second World War, 1939 and 1947. So they point this out with two of these. Now be careful, this is where we sometimes get tricked. there is a general, um, there is a, there's really not a large amount of scatter. So we're going moderate scatter. And so I think they added in this moderate scatter part. There's really not a large amount of scatter. Scatter is how far the points are. And I do see the general linear trend. There's that gap there, there's that gap there, and there's a little bit of non-linearity here at the start, but a lot of it, especially here, there's huge linearity. That's very linear. Starting to level off a little bit. But there's really not a large amount of scatter. So larger scatter means the points are spread out more. This would probably have a moderate amount of scatter. Find the regression equation right here. This is where you would never do this by hand. We have right here the regression equation already saved for us. If we go to the red arrow and go to fit line, by going to fit line right here, it adds the regression equation for us. And we have here negative 247.89 is the intercept. And then we have right here the slope is going to be the following. Round to 2 decimals. Go down right here, round to 2 decimals. And we are good to go. That should do it. Are the conditions met? This is where this question, I think, goes a little bit sideways because we kind of have an issues with the straight enough right here. And I think they highlight that for you. No, the relationship is not straight enough in the early part of the 20th century to fit a regression line. The variables are quantitative and there are no real outliers. So I've always had, you have not completed. Oh, no. Oh, wait, we don't want to submit the quiz. We want to check the answer. This has always been an issue I've had with this question. Slowly, I'm remembering the tricks right here. It's generally linear, but there is a bit of an issue. They're not saying it passes the condition. They're then noticing this at the start. So that is a problem, but do realize right here, we do mention the gaps. So there are gaps in the data. And then the moderate scatter right here, rather than the large scatter, was a giveaway from me to help me choose between those. So pretty good question, and helping you identify the notation in the jump output right here especially. We've got the R squared, very high R squared, and the significance of the model down here. In institution reports, let's go check that one out here. We found it. I don't know if I've done this one. Let's go check this out. In institution reports. So here we go. 104. 1. You're welcome. In institution. Okay. In institution reports many demographic statistics about countries of the world. Data were collected about the fertility rate, birth rates of women, and the female life expectancy in years for 200 countries of the world. The regression output in a scatter plot of the data are shown below. Complete parts A through D. Are the conditions for the regression satisfied? Well, you've got a huge outlier over here. Remember, when we do regression, we always want to do QQ straight enough, no outliers. So this is the regression plot itself. And when you take a look at it, it is 2 quantitative variables. You have to have that to get a scatter plot. So virtue of it being a scatter plot, it meets that. I do see part of plot thickening issue. It may be getting a little thicker, but there is a big outlier. It's mainly straight enough. And if you want to really go for plot thickening, I don't know. If they're saying there's plot thickening, this isn't the worst. Plot thickening is when the plot gets thicker in certain areas. Now, don't look at the outlier for plot thickening. For plot thickening, you want to look at the overall thickness of the plot, and residual plots are really great for that. Hint, hint, hint for the test. There is an outlier over there, but overall, we see that there's not too much plot thickening. I hope they don't say there is. So let's see if they do get into that. Oh, they're only talking about the residual plot. The residual plot has much more variation for large predicted values. The residual plot is reasonably scattered. The residual plot contains clumps. No. The residual plot shows, no, it doesn't show strong nonlinearity. The residual plot contains clumps. I never talk that way. The residual plot is reasonably scattered with no evidence of nonlinearity, so it's appropriate to fit a regression model. That is about the best, but let's look at the first again. The residual plot has much more variation for large predicted values. No, I don't like their answers, but we're going to go with that for the moment. Is there an outlier? Yes, there is. Yes, an outlier occurs at this. The outlier has an unusually high, it's way above the model. If you look, a linear model, it's unusually high, and you can actually see it down here with the residual plot too, but the line would go through here, and this has a very high residual. It's way above the predicted value. So with that right there, it's way above what we would predict. The LR has an unusually high life expectancy, and it occurs round to 1 decimal. This is where you have to look in here. That's where 7.5 would be at. So it's about 7.7 or so. They're probably giving a little leeway on this. Okay. Interpret the R-squared values. This is 63% or 63.7% of the variation in life expectancy is explained by the variation in fertility. So 63.7% of the variation in life expectancy is accounted for by the regression on fertility, on birth rate, which is fertility, which they just said fertility right there. So I usually say 63.7% of the variation in life expectancy is explained by the variation in fertility rate right there. Yeah, you bet. We got more time. So if a government leader wants to increase life expectancy, should they encourage women to have fewer children? No. That's correlation is not causation is what they're getting at. So we could probably look for that phrase right here. Trying to see if I see the phrase correlation is not causation. Although there's an association, there is no expectancy for causality. So you kind of got it right there. Yeah, Reed, you got it. Lurking variables may also account for this. So there was one I was concerned about. It was like the first one, right? Oh, but we got it right. I didn't love that first answer. I would say the model looks good except for an outlier. But they're mainly talking about the residual plot. And we talked about that early on. And we said the residual plot really had no issues. It doesn't have plot thickening. And the line looks to be going pretty good. The line is actually where 0 is at because anything on the line would have a 0 residual. And the points look to be evenly scattered around 0, which is what you want right there. So good questions. A student who has created a linear model. Let's go find that one. So many questions. Here we go. A student has created a linear model. Student who has created. Okay, let's. Oh, was I zoomed in this whole time? Hope it wasn't. Ooh, go see that. Okay, a student who has created a linear model is disappointed to find her R-squared value is very low at 13%. So she's only explained about 13% of the variation. Does this mean that the linear model is not appropriate? We don't really judge things by R-squared by that. The line is, does the line go through it? Here we go. No, there is no value of R-squared that must be met in order for a linear model to be valid. To determine whether the linear model is valid or appropriate usually involves the context which data was collected, or looking at the scatter plot. Yeah, no, we're not going to look at R-squared for that. No. R-squared is the percent of variation explained. Does this model allow the student to make accurate predictions? It's not really. R-squared is pretty low, so very little of the variation is explained. So no, a low R-squared value indicates that there is a large amount of variation around the regression line, which implies that accurate predictions are difficult. That sounds pretty good. No, the model does not allow the student to make accurate predictions because the R-squared value does not exceed the minimum. There's no minimum. There we go. R-squared is just the percent of variation explained. I would preferably say we don't explain a lot of variation. So this would not be a very good model because it only accounts for 13% of the variation in the Y variable of interest. In justifying his choice, another question time. So many, is there any evidence? Here we go, in justifying his choice. And let's mark the question. In justifying his choice. Okay. In justifying his choice, a student wrote, I know this is the correct model because R-squared is 99.4. Well, you might have overfit. That's a complex topic for another day. The scatterplot should be examined first. Yeah. No, it doesn't mean it's inaccurate. The reason this is really a complex question right here, because what they're getting at is you could have something like this right here. Here we'll do x, sure, x squared, but we need an x squared here in a moment. X squared, x, 1 through 100, and then random. Yeah, you bet. Random norm 100. Okay, so let's go ahead and plot this, or do m save into lm. And what we're doing here is we're creating a model which probably has a very high r squared. So this guy provide. Oh, we did. I think we did the gestation one just a moment ago. And take a look at this right here. So there's the linear model, and the r squared for this model is 93.8 or 94%. So when we look at this one right here, the r squared is 94%, but this is not the appropriate model. Why? Why is the line not appropriate here? Why is the line not appropriate here? Why would the linear model not be the right model? Oh, it's a different one? Yeah, we'll do it here next read. You got it. It's nonlinear. So we would need to take a look at the scatter plot. That's kind of key to these questions. The scatter plot should be examined first. Don't just look at the r squared. Does this model allow the student to make accurate predictions? Yeah, so generally you're going to get pretty good predictions. No, we don't want to say the line fits the data. We can't say that. But a high r squared means we've explained a lot of the variation. So probably, but there could be outliers. See, this is the only one. No, the linear model might not fit the data everywhere. Well, that's kind of true for everything. This is wrong, just categorically wrong. This is wrong. The only two possible answers are these, and we're going to go with that. And that says it's wrong. So, yeah, that one is where it gets a little bit ridiculous. What they might be going for also is they could be going for something where you could have data that is very, very... It's like, yeah, maybe they're right. Oh, I got to go to the original screen size for this. So let me go to view. That's the first one we missed today. No. So they might be going for something like this right here, where you get an r squared very high of 97%. So it's not making accurate predictions at the bottom. It's just fitting to an outlier. So you could get a very high r squared of like 95% by having outliers and stuff like that pull the data in a direction. The linear model might not fit the data everywhere, which is consistent. We should look at the scatter plot. But does this model, I would say probably. It explains a lot of the variation, but we don't know how many points there are. We don't know if there's outliers. We don't know if it's nonlinear. We should probably investigate the scatter plot first. But it does explain 99.4% of the variation. So they tricked me. But hey, Jesse, good to see you here. If you have time, could you go over the student, a student who has created a linear model? Let's go do that one here. Students create a linear model. First one we got wrong today. No! They tricked me. It's like, is it generally good? Yeah, it's probably generally good. Student created a linear model. What chapter is that on? A student who has created a linear model. What chapter is that on? I think there's the any evidence of gestation one. Gallup poll. Wait, the Gallup poll. Which one are we doing next? Because I thought we had a few here. If you see a number, tell me which one to do. The scatterplot shows the gestations. I think, yeah, here it is right here. Here we go. This one right here. We got one. The scatterplot provided. 13. Nice. Okay, let's go ahead and do this. Good job, everybody. Let's do this. Chapter 8, number 13. The scatter plot provided shows the gestation periods and life expectancies for several animals. Yeah, I think so. The plot contains 2 points that may have been concerned. The point in the upper right, elephants. There's elephants and hippos right there. And let's take a look. By removing one of these points, we can make the association appear stronger. Which point? Okay, so which of these does not follow the trend? Elephants or hippos? So the trend in the data is like that. Which of these is further off the trend? It says we can remove one of these points and make it stronger. So which of those points could be removed to strengthen the trends? Hippos. So if we remove hippos, there's going to be a stronger trend in the data. So key right there, removing hippos would make it stronger. By removing hippos, we would make the association stronger, since hippos are more of a departure from the pattern right there. Hey, Sydney, good to see you here. Would the slope of the line increase or decrease? Now, this is a little bit tough right here. Okay. So you have to think of hippos as having a gravitational pull. So is hippos pulling the line down right now, or is it pulling the line up? Currently, does hippos have a downward pull or upward pull on the line? It has a downward pull. So if we remove hippos, then we remove the downward pull, and the slope would go where? So if we remove hippos, we move its pull on the line would go where? Because hippos has a downward pull. And you just have to think about it as like a teeter-totter, like over here is the fulcrum, and hippos had a downward pull on it. So if we remove it, the line would go up because the point is no longer there to pull it downwards. Little tricky on that. So it would increase because it's below the regression line and technically above the mean of the x's. They should mention that. See, now we're telling my Pearson what they should mention. Should we just keep removing points to increase? No. These are such wrong answers. Should we just keep removing animals to increase the strength of a model? All data points for a model should always be kept. No. Data points that aren't similar to the mean values should be removed. No. Only data points that strengthen models should be kept. No. This one I'm a little bit concerned about. You can only remove some points, and you have to have good justification for removing points. That's a little bit iffy on the answers right there. The slope of the regression line is 15.5. If we remove elephants from the scatter plot, the slope of the regression line is 11.6. Do you think elephants were an influential point? Influential just means it's influencing the slope. So since it changed it by this much, as in the slope went from 15.5 to 11.6, yes, it is removing it. Yes, removing it lowered the slope significantly. And let's see if we did get that other question right. I was very worried about this question right here because it was just worded weirdly. I would say we need very good justification for removing outliers. So sometimes I don't like the exact way they word it, but I would say if you're going to remove outliers, you need very good justification. You can't just be like, I don't want this point. I don't want this point. You have to have strong justification. The scatter plot provided shows. Nice. Let's go grab it. We've done a lot of these today. I think we did more earlier. Someone say Gallup poll? I think someone said Gallup poll earlier. We should do the Gallup poll one. That's the one we just did? Okay. Is there any evidence animal gestation? I think we might have done that one. Let's see. Yep. Here we go at 39 minutes in. Is there any evidence in animals gestation period? Yep. Right there. Is there any evidence in animals gestation period? Yep. Check that one out at 39 minutes. We're going to keep going along. Gallup poll someone asked for. Let's do it. We're going to get as many done as we can. What do you immediately notice about this data? What do you immediately... Thank you, Reed, right there for trying. No worries, Ethan, 100 points. Thank you for asking. What do you immediately notice about this data? You're welcome, Kelsey. The Gallup poll. What do you immediately notice about this data? Has a slight curve. Great answers, Jesse, right there. But it's got that little bend at the beginning. So you always want to think QQ straight enough, no outliers, plot doesn't thicken. It might have a little bit of plot thinning at the end, but right there. So there's this bend at the start. It's pretty good. QQ, problem was straight enough, it looks like. Is there a clear pattern? It has been decreasing. The percent of adults who are smokers decreased dramatically and linearly the entire time. No. The percent of adults who are smokers did not change much. Yeah, look at that. Where the numbers of smokers started to decrease dramatically linearly until the end of the graph. Yeah. 70s is about here, and it was relatively flat, and then it goes down. So if we go to the 1970s right there, we go to the 70s, and that's probably pretty good right there. So I think that's got it. It was relatively flat at the start, and then it went down. But yeah, until the 70s, it didn't really change. Is the association strong? It's very strong throughout. Strength right here is going to be how tight it is around it, and we're just looking at the tightness around it at all points, and it stays relatively tight at all points. So if you're strong, it's going to be equally strong throughout, I think. The association is about equally strong, so it stays relatively, it's relatively strong. It's not weak, it's not vague. Equally strong, exactly. Great job, Kelsey. Because the strength, once again, is the tightness. So it's about, these are the bands I'm drawing around it right here. Like when I do this right here, I'm measuring tightness, and it's about the same tightness throughout. So it's about equally strong even at the start and finish. Doesn't take into account the form of it. Is the linear model appropriate? No, a linear model would not be appropriate throughout, although one could fit a linear model after 1970. I think we've done it. Uh-oh. Was it the middle question? No, it's not that one. It was the first one, was it? Wait, what? The association appears a week before 1970s. I guess because it's flat. Well, there's the one we missed. But what they're saying here is, and they're kind of got a point, I have to give it to them. This is no association when it's completely flat, because X and Y, if X and Y are flat, then there's no relationship between X and Y. So I do have to give it to them. That was a complete error on my part, not me disagreeing with Mike Pearson. I think they actually got that one correct, because when X and Y have a flat relationship, there is no association. So the scatter there really doesn't matter, because you could have things like this that are very tight around a flat line, or you could have things like this that are very scattered out around a flat line. But each of these would be no association right there. Does that make sense, Kelsey? Sorry for that little bit of a mess up right there. But at the start of the graphic, there's really no association because it's not going up or down. It's flat, which we did acknowledge. And because of that, a flat line is no association between X and Y because there's no relationship. It's a slope of 0. So that is correct right there. And then afterwards, the association appears week before. And then they should mention it's fairly strong. That's where they tricked me because I was looking for all the strong relationship stuff. It is fairly strong afterwards, though. An analyst tried to fit. Yeah, let's check that one out. Here we go. An analyst tried fitting. Oh, there it is. We are going through as many questions as we can. We got a lot done today. Okay, looks like a simple one. Let's check it out. An analyst tried fitting a regression line to each segment of a data set, separated to a test model of the whole data, and found the plot given below. The model tested gave the equation of predicted January value equals to the mathematics times December. And whoa. I don't think I've ever seen this one. So they're fitting different models. Okay. What does this say about the analyst's concern about the model? Were they justified in worrying that the overall model might not be accurately summarizing the relationship? Briefly explain. Oh, because they fit it to different segments of the data. Ooh, so each segment of the data has different. Oh, so this is such a. So they fit here like 5 different regression models. Let's count. 1, 2, 3, 4, 5. Yeah, we go up through here. 1, 2, 3, 4, 5. They fit 5 different. Sometimes they got a negative slope. Sometimes they got a positive slope. This is really complex, but an analyst tried fitting the regression model line to each segment of data separated to a tested model below. The model being tested has this right here, so it has a positive slope. So with this right here, they follow, okay, each segment has a different best fit line, so they follow different relationships. Why did they do the model being tested? What does this say about the analyst's concern about the model? What was the analyst's concern? Were they justified in worrying that the overall model might not be accurately summarizing the relationship? Yes. They are justified because the models are very different. So looking at this right here, some models produce negative slopes, some models produce positive slopes, and the overall model has a positive slope. So we're really seeing a lot of variation in what's possible here. So yes, each segment has a different best line of fit. Yes, they are justified in their concerns that the overall model is not being summarized well. They follow different relationships. That is very tricky. Because what you would want is if you did it on different segments, so they're basically subsetting their data to get very similar models, but they're getting very, very different models and showing that there's something that makes the model differ. So this right here would be of concern to somebody because they'd want their models to look like the model they fit. Very complex question. Don't think it has a big learning objective, but it's showing you kind of how statisticians do stuff. This is test and holdout data, but it can be answered because the key thing here is, were they worried in justifying their overall model might not accurately be summarizing the relationship in the data? So here's the overall model. You can see the slope's positive, and then down here when you look at it, some of the slopes are negative. There's one negative slope. There's a flat slope, meaning no relationship. We checked that out just a second ago. And so they'd be justified in thinking, do I really have this relationship explained well? Do we have one or two more? We did a lot of questions down here. We've done a whole lot of questions today. We might take a break before class because we got a lot knocked out right here. We got, look at all those Chapter 8 questions done right there. Let's see. Well, might head off here and take a break before class. Any other last questions here before we get done before class? We might take a quick break. But with that, swing by class, ask questions, keep working away. Until then, bye for now, everyone. You're welcome, Reed. Great job. Keep working on the assignments. You got this. Bye.